Good afternoon, bon après-midi, everyone. Welcome to this edition of the McGill Physical Society Colloquium. I'm coming to you live from the brutalist majesty of the Rutherford Physics Building at the foot of Mount Royal in the heart of Montreal. I just have to remind everyone who is in the Zoom session that you are being recorded and streamed live to YouTube. If you do not wish to be recorded or streamed live, please log off of the Zoom session and join us on YouTube. I will quickly explain the plan for the colloquium today before I pass off to the host who will introduce the speaker. Today we will have a 45-minute talk followed by 15 minutes of questions and answers. After the 45 minutes plus 15 minutes, professors in the audience will be asked to log off for our après-colloque. The après-colloque is a chance for undergraduates, graduate students, postdocs, and others to get to know the speaker in a more intimate setting. At the time of the après-colloque, the recording and live stream will be stopped. And so you will have the opportunity to talk in a more private environment. I have to remind everyone in this session, in the Zoom session, that you have the ability to unmute yourself, mute and unmute yourself. So please do not unmute yourself during the talk or at times when you're not called on. If you do, you may be removed from the session. Before I go forward, I'll just let you know how the question and answer period will go. So to ask a question in Zoom, you should raise your hand icon in the Zoom session. The raised hand will move your name up to the top of the participants list, and I will call on you one by one. At the same time, you can ask questions from the speaker at the end of the talk on YouTube by typing them into the chat. And those questions will be relayed by my associate to me, and I will ask those questions one by one as well. OK, so with that, I'll pass off to the host, Professor Tammy Parrig-Barnea, to introduce the speaker.
Okay, hi everyone, and welcome to McGill's Physical Society Colloquium. It is my great pleasure to introduce today's speaker, Professor Phillips from University of Illinois at Urbana-Champaign. Philip did his bachelor's degree at the Walla Walla College. At that point, he had the pleasure of introducing himself as Philip from Walla Walla, which is, as you can see, a tongue twister. However, soon after, he moved to do his PhD at the University of Washington, and after graduation, he was offered the prestigious Miller Fellowship to do a postdoc at Berkeley. When he finished the postdoc, he moved as a professor to MIT, and he worked there between 84 and 93. And afterwards, he moved to Urbana, where he's been ever since. Phillips' work focuses on understanding systems of many interacting electrons, and very often you'll find him exploring new ways of solving the age-old Hubbard model. His interests are very broad, spanning from high TC, iron-based superconductivity, boson systems, topological states of matter, and even the duality between cuprate superconductivity and the theory of gravity. He won many prizes and honors, too many to mention here, maybe just the Guggenheim Fellowship that he won recently. He is a fellow of the American Physical Society and of the American Association for the Advancement of Science. He wrote many papers and also a high-level graduate textbook on solid-state physics. But this is just his CV. That's not the main reason why we invited him. The reason we wanted to invite him is because of his style of work, his understanding of physics, and his personality. So personally, I met Philip when I was a graduate student at UBC, and he came to give a talk, and he talked about Mott insulators. And I think this was around the time when he coined the term Mottness, which I think many of us use ever since. It struck me then, and also in later times when I met Philip, that he is an original thinker. So he takes a problem that was addressed by many times by many other people and looks at it from new angles. And although his theory is full of state-of-the-art techniques, of course, theoretical techniques, and his calculations are involved, he can present his idea in a light and even entertaining matter, which I'm sure will be the case today. So Philip, welcome to McGill, and the stage is yours.
Please unmute, Philip. You'll have to unmute, hover over the microphone.
Yeah. Sorry about that. Thank you, Tammy, and thank you for the introduction. And it's interesting how people see you. I will try to live up to this, to the expectation that Tammy has no doubt put in your mind. So I'm still working on Mottness. I'll be working on that for the rest of my life, I presume. And I'm going to put superconductivity and Mottness together in a way that I never thought I would previously. Namely, we obtained some exact results. And I think it surprised the referees that anyone could obtain exact results in these two things. I think that's largely why our paper just appeared in Nature Physics. Here is the online reference. And there is a news and views on this by Jan Zanen. And this work was done with two of my colleagues, a grad student, Luke Yale, and Edwin Huang, a postdoc at Illinois. So since it's a colloquium, let me start at the beginning. Let me tell you what superconductivity is. Oh boy, I have to get out of this because, oh, it worked. Okay, good. Okay, so superconductivity.
You're no longer sharing your screen, Philip. You'll have to.
Oh, I'm not sharing the screen. Okay,
yeah,
I'm sorry. Yes. Anytime you mess with this, with any of these buttons, you lose this. Okay, is everything fine now? Yes.
Yes, now we see it.
Okay,
fine.
Good. So superconductivity is the phenomenon of the vanishing of the electrical resistivity, or the resistance. And this was discovered in 1911 in Mercury. And the inkling as to what might be going on was outlined in a very elegant paper by Cooper. And what he did is he said, let's consider two electrons joined together above the chemical potential. Okay, it is not advancing. Share screen.
So it sounds to me like you need to make sure you have the focus on your presentation software if you're using PowerPoint. Probably.
It's in Keynote. And
oh, okay. Or Keynote, then maybe you need to make sure that you click on the Keynote window.
It says one person can share at a time. Are you sure?
We're not sharing on this side, so you should
be
able to share. I'll click multiple participants, but I don't think that's a good idea. We'll see.
Okay, yes. So sorry about that. Cooper considered two electrons outside the Fermi surface, and he turned on an attraction between them. And what he found is that that's not the ground state. They actually want to form a bound state below the chemical potential. But the problem with that is that there are no spaces below the chemical potential. So this posed a problem. So what it's telling you is that there is an instability. Okay, so it seems as if I can't advance more than one slide at a time.
So in the worst case, I think you can go out of presentation mode and share just the screen of your presentation, and then we would see the little stuff on the side, but you can still go through the slides.
Well, that's not very optimal, is it? Why is this happening? We tested this before we started. problem is I have motion and I need to sort of be able to do that.
Okay, I have a suggestion from a little bird told me that you might try advancing by mouse click. That might help.
Mouse click.
Instead
Okay.
of using the forward arrow.
Okay, let me try that. Oh, that works. Okay, well, it worked so far. Sorry about this, okay?
Thank you, little bird.
Yeah, okay, so what this suggests is that perhaps this Fermi surface is unstable to a condensation of 2e. And to represent that, you can say it has an amplitude and a phase. There's a deep connection between this Fermi surface and BCS theory of superconductivity. Let's say these are the energy levels in a non-interacting system. The key tenet of Fermi liquid theory is that there's a one-to-one mapping. If you turn on any repulsion you want, as long as it corresponds to something local in real space, you turn out any interaction you want, there's a one-to-one mapping between the states over here and the states over here. And this one-to-one correspondence can be summed up in a very elegant way by simply saying that this repulsion that you added is an irrelevant perturbation. It does nothing to this correspondence. The only thing that destroys this correspondence is turning on an interaction when electrons are on opposite sides of the Fermi surface. And this is the key behind the whole BCS theory. So we say that BCS is a solved problem because we understand the state before you added this, and we understand the state after it. And the key quantity in BCS is this ratio of the gap to TC. That's 3.5. That's a number I want you to remember. The only number you have to remember in the whole colloquium. Okay, so here is the evolution. You start with a Fermi gas, a very simple thing of electrons just filled up to some point. We have Fermi liquid theory, in which we have the ability to create quasi-particle excitations, and those things can pair up, and you form a BCS superconductor. The question I want to ask is there anything beyond this? Now, if there is physics beyond BCS, there has to be a new fixed point. And it has to be beyond Fermi liquid theory, because we know that Fermi liquid and BCS go hand in hand. There's reason to believe there is such a fixed point out there because of the copper oxide superconductors. These copper oxide superconductors start out their lives as Mott insulators after Sir Neville Mott. And the question Neville Mott was trying to answer back in the 30s is, why does nickel oxide insulate? It's D8. They're unpaired. It's an open shell, and if it's an open shell, if you just use band theory, that should completely be a metallic state. But these systems actually insulate, so these things, the electron should just be able to hop around. So what Mott said is perhaps it costs a certain amount of energy when an electron tries to go a place where another electron is. And so in other words, there is an energy cost anytime you try to occupy two electrons, put two electrons in the same region. And perhaps that opens a gap. And if this opens a gap, without changing the size of the Brillouin zone, this is all real space physics. Perhaps this is why nickel oxide insulates. Okay, so all you have to do then to solve the copper oxide superconducting problem is solve the Hubbard model, the model I just outlined, a model in real space which has this local interaction and hopping. Very well-defined problem. You solve that, you illustrate the Cooper instability, and you're done. The problem is you can't do this. It's an intractable problem. And there's been a lot of discussion of how you might solve the problem. Here are some acronyms for various ways in which people have tried to solve the problem. But the key thing is there are lots of disputes. And as Tammy was alluding to, there's a famous dispute which has really shaped my thinking on the problem, and that is what I keep coming back to. And it's a dispute between Bob Laughlin and Phil Anderson. And what Bob Laughlin's point is that all of this talk of Mott insulation and a gap opening and creating what's a lower Hubbard band and upper Hubbard band, all of this is just vague nonsense. And we should just stop talking about that. And the rejoinder to this is the paper that Phil Anderson wrote, A Critique of Two Metals. And he just rephrases what Bob Laughlin says. 10 years of some of the best minds in theoretical physics have failed to produce any formal demonstration of the Mott insulating state. And then he says, the statement would be ludicrous if it were not so influential. And he goes on to say, it's certainly a tragedy of Mott that although he almost certainly won his Nobel Prize for the Mott insulator, Slater, who couldn't think clearly about finite temperature, won the publicity battle. Okay, now what does he mean by this? And why is Bob Laughlin so upset? So here's Laughlin's objection. Mott was arguing for, without breaking any symmetry, that you can change a non-interacting band into two bands without changing the size of the Brillouin zone. And this would be a charge gap. So what you'd be saying is that each K state in here would somehow be living at both energies. And there would be a gap somewhere in the middle. And this means that you're going from 1 to 1 to 1 plus 1, which is 2. This would certainly destroy the Fermi liquid correspondence between one state over here. Okay, and this is what Laughlin said can't happen. Okay, so I decided to ask myself the question, okay, this is the dispute. I think most people ignored this or didn't really, they just viewed this as just it certainly had great entertainment value, but you know, I'm a serious guy, so I said, okay, there has to be something that you could put your finger on that if you were to clarify, it would settle the debate. Okay, so I decided that the difference between them was Mottness. And if Mottness it means anything, there should be a certain quantity you can calculate, which would tell you if Mottness is present. And it turns out the problem comes down to zeros, the simplest of all numbers. The quantity which is 0 for Bob Laughlin, for Phil Anderson, is the real part of the green function. For Bob Laughlin and everything he was thinking about, the real part is not equal to 0. So it's a very cut and dry thing. There's no ambiguity here. So I need to explain what the real part of the green function is. So let me do that by counting particles, and you'll see why I'm doing this. So how do you count particles? Well, you just put labels on them. 1, 2. This is rather tedious. So is there a more efficient way of counting particles? Okay, so I want to define a certain quantity, and I want to explain what the Luttinger counting theorem is in terms of the quantity that I'm now going to define. So let's look at this quantity right here. It's just 1 over a function, and E is the probe energy, epsilon P is just the energy of a particle. So clearly whenever E is equal to epsilon P, this thing is 0, 1 over this thing is infinity, which means this is a good thing to look at if you're counting particles. So let's look at the behavior of this function in the vicinity of epsilon P. It's negative for E less than epsilon P, and for E bigger than epsilon P, it is positive, as you can see just right here, which means if you just count the number of sign changes that this function encounters as you simply track E along this axis, you will be counting the number of particles. You'll be counting the number of poles. Each pole is telling you about a particle, and hence, if this is just the step function, where this quantity is positive defines a series of a locus of points in momentum space. Each one of those is counting a particle. That should be the particle density. Now, written in this way, I've actually complicated the problem, because the Heaviside step function just is non-zero anytime this argument is positive. It doesn't care the mechanism by which this function becomes positive. The case I've outlined here is when you have poles. But there's a simpler way in which functions can become positive. They can simply just cross the real axis from negative to positive. This is a zero. And that's entirely allowable in this counting of a physical quantity, namely the particle density. Now, a zero crossing cannot happen for any function of this form. This will only give rise to poles. But technically speaking, these are possible. So what are zeros really telling you? It's telling you that you don't have any propagation. If you don't have any propagation, there's no pole, which is a breakdown of the particle concept, and that is the key thing in Mottness. Okay, now what Mott was after is a spectral function which looks like this, in which you have a split, you have a schizophrenic distribution to the density of states. There's some here, above and below the chemical potential. Now, just using Kramer's Kronig, I can construct what the real part of the green function is. And it's just this integral, this weighted moment of the imaginary part of the green function over omega. Now, this quantity is entirely positive. This is the thing that's changing sign, which means there will be some contribution below the gap and above the gap. Below the gap, it will be entirely negative, above will be positive. Negative and a positive number can certainly balance out to give you zero. So zeros are really about the fact that you split the spectral weight of each k-state into two distinct regions. So it's a balancing between spectral weight at high energies and at low energies. And that's why zeros are fundamental. And this is happening without breaking a symmetry. So zeros are telling you about gaps in strongly correlated systems. Of course, Mott didn't know about this. This came many decades later. Okay, now if we'd done this with symmetry breaking, these would be in different bands, which means your green function would just look like this. The determinant here is just a product of this times this. Well, that can never be zero. And that's the sharp difference between what Laughlin was talking about and what Anderson was talking about. Okay. So the problem ultimately, or the deep problem that Bob was alluding to, is where's Mottness? Because he knew of this argument, that if you start with the Fermi surface, all the interactions that you add are completely irrelevant. So where's Mottness? Okay, that's ultimately the question he was asking. He didn't state it in this way, but this is a sort of an elevation of his complaint. So what went wrong? Okay, so here's the Hubbard model. No one can solve the Hubbard model. The only demonstrations of this we have are completely numerical, which tells you if you're going to say you've solved the high TC problem, you can't start with this, because you'll never make any statement that will be so clear that no one will doubt it. So I want to ask a question. Is it possible to think about Mott insulators differently? In particular, rather than thinking about them in real space, which is what everyone will tell you, can you do something you're not supposed to do? Let's think about the problem in momentum space, the completely opposite regime. Okay, and if you do, what can you learn? Okay, that's exactly this model, which was written down in 1992. And if Bob Laughlin had done his homework, he would have realized that, in fact, you can define lower and upper Hubbard bands. Okay, so this is just the standard hopping term, which is in the Hubbard model. No one has any disagreement on that. What is new here in this model is that the 4 fermion interaction is not the traditional one. It is an all-to-all interaction. It's not random, as in people have been talking a lot about these things, the SYK model, but it says the center of mass is preserved. Now, I don't know if they derived this model by reverse engineering, But those of you who can do Fourier transforms in your head know exactly why this model was written down. If you introduce CK as this and simply Fourier transform, this model reduces to something very simple. It reduces to something which has the standard kinetic energy, which just depends on the density. And now this term here is completely diagonal in the density. It's just a contact interaction between upspins and downspins in the same density state, in the same momentum state. And the key thing here is that this is a relevant interaction relative to the Fermi surface. And this was not considered by Polchinski and Shankar et al. In all of their schemes because this corresponds to a non-local interaction in real space. And remember, I said real space, I mean, to just simply local interactions. Okay, so the generalization of this model is this. Anything of this form has a certain property. These are all relevant perturbations, and this term clearly commutes with this term. Any model in which the kinetic and the potential energy commute is completely solvable. And hence you can write down the green function for this. And even in a colloquium, I think you can still see the solvable Mott transition. It's a very simple function. And it has these two bands. This thing defines the lower Hubbard band. This one defines the upper Hubbard band. Okay, now what this means is that you can define the electron operator, which creates a state in a particular momentum state with a given spin, as a sum of two possible terms. This one is living at low energies, this one's living at high energies. And you can put them under the same energy denominator, and this is what you end up with. So you have these two terms, and you simply added them together, but you've rationalized them over one denominator, which means this no longer looks like that simple function I wrote down, 1 over E minus epsilon P. There's a possibility that you might engineer zeros here. In fact, you can. If you just look at this function right here, which is what makes the dispersion deviate from the standard non-interacting case, this you can view as the self-energy. Although strictly speaking, it's not, because it can actually blow up. This quantity is singular anytime the omega equals this quantity. So this is defining a series of points, a locus of points in momentum space, where this is infinity. If this is infinite, this is in the denominator, your green function is 0. Which means although this model is simple, and the potential and kinetic energy commute, it has zeros, which is the non-trivial thing you need to get Mott physics. Which means nowhere is there a Fermi liquid, and we've generated a completely solvable model which has zeros. Okay, and this model was written down in 1992, and the paper has received, I think, 25 citations. And as the abstract says, our work has generated roughly a fourth of those. So this is not a well-known paper. Okay, there's a Mott transition. And the transition has a natural gap anytime this repulsion between electrons in the same K state, when this exceeds the bandwidth of the problem. And here we go. This is the surface of zeros, because now the spectrum is split between something here and something up here. These all have well-defined algebraic expressions. And note, this zero surface is symmetrically located between this and this because the chemical potential lies right in the middle. That is the Luttinger surface, the surface of zeros. Now, if you go slightly U less than W, this band will actually, both of these things will cross the chemical potential. And now the region which has the zeros has to be the singly occupied part. Now in a Fermi liquid, there's no singly occupied part. You either have completely occupied states or empty states. what Mottness is doing is it's giving you a singly occupied part, and mirroring the singly occupied part is a surface of zeros. Here, as you dope this, as you let U be less than W, the singly occupied part or the Luttinger surface is this part right here. So it's shrinking. This part right here is, yes, that's the Luttinger surface. And here are the occupancies, or the fractional occupancy, meaning per K-state, not including spin. This part is 0. This part is singly occupied, or each K-state is half filled, and this region is doubly occupied, or each K-state is singly occupied. I mean, each per spin that is. Okay, so that's the key thing. We have a trifurcation of the spectrum into 3 distinct regions, and you can assign the occupancies. And to reemphasize, in a Fermi liquid, you cannot get this region. All you have is this or this. Okay, now, when you dope the system, the region where you have single occupancy shifts, and in all of this, you can calculate the region over which you have sign changes of the green function. And here it is. You're supposed to end up with 1. But as you can see, there's a huge deviation from this purple region, and that means that the standard way of enumerating the charge density in the system by counting sign changes of the green function doesn't give you a one-to-one correspondence between the charge density and the sign changes. And it's because we have zeros. The problem with zeros is that unlike poles, there's no physical consequence when a 0 crosses the chemical potential. And hence, you shouldn't be counting them. They don't really contribute to the charge density. Okay, so what we have in this Hatsugai-Khomoto model is the following. We have a trifurcation of the spectrum into empty, singly, and doubly occupied, doubly occupied regions. So to look at our evolution, we start with a Fermi gas. You have a Fermi liquid, and these quasi-particle excitations are useful in understanding how the system can condense into a superconductor. And now the terminus of this evolution is a dope Mott insulator. And this is Sir Neville Mott. So the terminus of this evolution is Sir Neville Mott. I wish you were alive today to see this evolution, but he isn't. Okay, anyway, so this is Mottness. Okay, so the question I want to ask now is, what happens to superconductivity? Because we have an exactly solvable model that gives you Mottness. What happens now if we turn on superconductivity? Okay, so the key point I've made so far, if you have a Fermi liquid and you distort it with this interaction, you can go through the standard arguments outlined by Polchinski and Shankar, and you can see that this term is actually more relevant than anything they considered, and Hatsugai-Khomoto lays plain that this thing gives rise to a Mott insulator. Okay, now what does this model leave out? It has to have left out something, otherwise it wouldn't be solvable. Okay, now what I want to tell you is that what it leaves out is, let me just evolve this. Here you have one empty site. As you evolve this thing in time, because the Hamiltonian doesn't respect the number of empty sites, the number of doubly occupied sites, you can generate more empty sites. But every empty site you generate will be paired with a site that's now doubly occupied. This is dynamical spectral weight transfer, and it's coming about from the non-commutativity of the kinetic and the potential energy. This is not in the Hatsugai-Khomoto model, but such terms are a T over U correction. So it's giving you the big physics correct, it's throwing away something that looks like this. Now, this is the other thing that you have to remember. Okay. Now, regarding superconductivity, an ex-postdoc was exploring insulating Luttinger surfaces in the presence of pair fluctuations, and he obtained the rather intriguing result that what you end up with is SYK physics. Okay, so what we want to do is see if this is true in general. So we turn on a pairing term on the Hatsugai-Khomoto model, and we write down a state that just pairs up electrons above the chemical potential. And we simply ask the question, is there a binding energy? If there is, this term had better be negative. And the condition, you can go and solve it exactly, is just this. And it comes down to doing one integral. And you're looking for E, a solution which E is negative. And here's the solution. There is a Cooper instability. And this is a limiting form in the limit that U over W is less than 1. So there is a Cooper instability. Now, the nice thing about this model is, as I said, it's super solvable. You can calculate the thing that everyone wants to calculate for superconductivity, namely the pair susceptibility. And you can go and do this exactly. This is just the susceptibility in the absence of this interaction. And all you're looking for is when this is equal to that, this thing diverges, that will define TC. And you can calculate TC for this model. And in the limit that W once again is bigger than U, you can obtain a closed form expression for TC, and here it is. In applying this formula, just be careful that W is bigger than U. It only simplifies to this in this limit. So this does not, for example, you can't set W equals 0 and talk about flat band superconductivity. Okay, now, that's just the beginning, because what made BCS famous is that they wrote down a wave function. And once they had this wave function, they could go and calculate everything. Okay, so I'm going to do a simple amount of algebra. This is a wave function which has this term U, this term V, and this is the weight of the creation of a pair of electrons. So this is a product, or this is the product. This is the sum of all terms having an even number of excitations. Okay, now I'm just going to rewrite this, restricting K to be positive. The reason I did that is this wave function, which everyone teaches, takes on a slightly different form. As Tammy has already told you, I tend to look at problems in a different way. But it turns out this is profound. And I'll tell you why. Because now you see that the distinct contributions in this wave function, this is singly occupied, this is doubly occupied, this is empty. Well, that's exactly what you need to go and write down a wave function for the Hatsugai-Khomoto ground state. Need a part that's empty, singly, and doubly occupied. So let me just erase this. This is what you're trying to model. So what this means is that you have to consider a wave function which has not 2 variational parameters, but 3. This term will describe the part that's empty. This next part will tell you about the doubly occupied part, and this will tell you the singly occupied part. So armed with this wave function, we can go and compute the expectation value of the energy and perform a minimization with these 3 variational parameters subject to this constraint. So we're just redoing BCS for these 3 things. And suppose, and hopefully we'll be able to solve for X, Y, and Z. Okay, let me just go back. How do I go back? Let's say I can't go back. Okay, so let me just go forward. The upshot of all of that is that you can get out an equation for the gap, and we already had an equation for TC. So this is the first result. And this has to do with the first thing I asked you to remember. I asked you to remember that the ratio of 2 delta over TC in BCS is 3.5. Now, you can see what the ratio here is kind of funky. forget about this stuff here. You don't really care about that. What you care about is this part. These exponents, which are the big thing here, all have different numbers here, which means if you take this ratio of delta over Tc, in the perturbative limit where G is just a small parameter, remember G is the interaction for the Cooper instability, the limit that G goes to 0, this ratio is infinity, which means this superconductivity is non-BCS-like. So that's the first result. This number is not 3.5, it's infinity. Okay, now, so this is so we know we have non-BCS superconductivity. Can we tease out more physics from this? Okay, now what BCS did is they didn't just tell you about the ground state. They told you about the excited states. And the excited states in BCS are particle-hole pairs. Now, these have a distribution which is roughly Boltzmannian. There are none of these in the ground state, because it's the ground state. That's why it's called the ground state. But these things exist at any finite temperature as long as you're less than Tc. Otherwise, that's not the correct ground state to be looking at. Okay, now, this quantity is different from the Fermi liquid dispersion because these things are gapped. So this thing is roughly the gap. That's what you're interested in.
You have about 10 minutes left. I'm sorry to interrupt, but 10 minutes?
That's fine. That's absolutely fine. Okay, so these are the excited states, and they're excited because they're separated from the ground state by a gap. Okay, now, since there are no excited states in the ground state, it has to be the case that if you apply this operator annihilating whatever these excited things are, call them Bogoloo bombs, you should end up with 0. Well, you can construct an operator which completely describes what these things are just by solving this equation. And they are hole and particle excitations. Okay? So this is really how you can say you've solved the superconductivity problem. It turns out for this problem, these aren't the excitations. The excitations here are something we call pions. And these are just our initials of my collaborators and my name as they appeared on the paper, because these excitations are not these things anymore. These excitations are in terms of the Hubbard band operators that relate to the lower and the upper bands, and there are 2 of them. Okay, so once again, you can perform the same algebra. Operate this on this new BCS state, you end up with 0. These things are gapped, and here they are. Here's the gap, but there are 2 of them now. So let's compare what we have. BCS, you open a gap. Here's the dispersion that I was plotting, and here it is right here. There's only 1 band. Now, in the case of superconductivity in a dope Mott insulator, there are 2 bands. So here is the shadow band having to do with the pions in the, so these are pions in the lower band, and here are the pions in the upper band. So now that we have superconductivity, we know there's always a high energy part and a low energy part. We can ask a very important question. Can we explain the color change, which people have seen experimentally in a cuprate superconductor? So here's the color change. The color change is telling you about the fact that if you integrate the optical conductivity up to some cutoff and call that number AL, and you call this number from the high energy part AH, these 2 things are trading off the moment the system superconducts. So here's the HAH part, this is going down, and right at TC, this increases in an accelerated fashion. And this is another thing which had always puzzled me, because it's telling you that the number of degrees of freedom at low energies is now tied to high energies, even in the superconducting state, which means Mottness is still showing up in the superconducting state. And if that's true, then these pions will play an incredibly crucial role in getting that physics right. And this change is around 3%. So we simply went and computed these things. Now, the reason why this is important is that the experimentalists noticed, although this is a small number, it's enough to explain the condensation energy. Okay, so the key thing here, we looked at this integrated lower weight over the weight when you don't have any superconductivity, changing the system parameters. And the key thing here is this number starts at 1 and increases. So this one thing is bigger than 1. And if you look at reasonable values of G, it's right around 2 or 3%. And the question is, why do we get this thing right? The moment you turn this on, the full Hamiltonian no longer is made of commuting terms. And what did I tell you about commuting terms, non-commuting terms? They have to do with dynamical spectral weight transfer, which means you're mixing doubly occupied and singly occupied sectors. Okay, and so we think this is a rather general mechanism that holds beyond the HK model, even in the Hubbard model. So this might be a general mechanism because it's always there. Okay, now the last thing is the superfluid density. Now, if you were to calculate the superfluid density in a Fermi liquid, this is what you would obtain. This is the filling in the band. It has to vanish when there are no electrons in the band, and it has to vanish when you have the whole band filled, because then there's no place to form a superconductor. So it has to vanish in the band insulator limit and the band empty limit. And so it should peak somewhere in the middle. Now we can redo this for our system because we have everything to go and calculate this quantity. And the answer is shown here. Well, it clearly has to look like the golden arches because the Mott insulator has to take over here and the suppression of the superfluid density has to happen in the vicinity of this Mott point. So because our system is governed by Mottness, we have a vast suppression of the superfluid density near the Mott point. And you can see it's a huge suppression. It's over a factor of 2. Okay, so this is a non-trivial result. So let me summarize. So this is a Mottness-induced suppression. Fermi liquid theory has had a great run. And if you know this paper by Polchinski and Shankar, anything you turn on that depends on form momenta is not going to destroy a Fermi liquid. Well, there's another axis I'd like to tell you about, and that's the terms which look like this. It turns out these are more relevant than this, and this gives rise to a Mott insulator. Now we're trying to prove that this really does give rise to a fixed point. And if it does, that's even stable to any kind of thing that you add. If we can prove that, then that would lend great importance to the Hatsugai-Khomoto model, and it will tell you the physics I've talked about survives even beyond the regime that I have, the context that I put it in terms of. So what this means is that we really should have been doing something we were advised not to do. And that is consider a Mott insulator in momentum space. And you would have thought that Mott physics is completely anathema to any construction in momentum space. You get non-BCS superconductivity. We have this growth of the spectral weight at low energies in lieu of the spectral weight at high energies. So the color change, this is infinite. There are a whole new set of new excitations in the system. So once you see that it's non-BCS and you have a wave function, you can go and compute everything. And it's very different, the superconductivity that arises when you dope a Mott insulator, at least the Hatsugai-Khomoto model, which has some consilience with experiments. So that is what I wanted to tell you. And I think that's 50 minutes.
Okay, thank you very much for that talk, Professor Phillips. So this is very nice. That's the final conclusion?
That is it. I'm sorry. It ended with a, I don't know what you can tell me. With,
oh, it's very good. It ended with a bang.
But that's the big conclusion. This is the big conclusion here. If we can prove that, then the problem is solved.
Yep. Okay, thank you very much. So if there are questions, please raise your hand if you're in the Zoom session. If you'd like to ask questions, I know there was a question that was entered in the chat already. Please use the raise hand feature to bring yourself to the top, and I'll ask you to unmute and ask your question. If you're interested in asking a question on YouTube, please type it into the chat. And of course, if you had some appreciation you wanted to show for the talk, type it into the chat in Zoom or in the chat in YouTube. So the first question comes, not surprisingly, from Professor Temi Pereg-Barnea. Temi, please unmute and ask your question.
It's the first question. I have many, but I'll just ask one because I want to give other people a chance. But so you showed us that the ratio of 2 delta over TC could be anything, basically. Is there a way for me to put realistic numbers into W, U, G, and all of that?
Yeah, I'm sure you could, but then you'd need to know what G is. And so, which is why I just focused on the bird's eye thing. BCS is derived strictly in the limit in which you've just introduced a small perturbation, G, right? So the only results you should believe are not when G is a huge number, but some somewhat small number. So the key observation here is G going to 0. These things have different exponents, and it's basically a large number.
You would advise against trying to make, some sort of a Uemura plot with it or something like that?
No, I wouldn't. In fact, that's a great thing to do. That is a great thing to do. Right. In fact, we could do that as a function of doping, I think. Yeah, that's right. That's a great idea. Yes.
Okay, thanks.
Okay, Temi, if you're done, please lower your hand. The next question comes from Yashar Komijani in Zoom. Could you please unmute and turn on your video, ask your question if you like?
Hello, thank you. Can you hear me?
Yes, absolutely.
Thank you for the talk. So actually, I just wanted you to clarify if it's possible. So the U term, is it diagonal in momentum or is it not diagonal in momentum? Is it NK or NK prime?
It doesn't matter.
Because that would be a Stoner instability.
Okay. The model we solved is one in which we had NK.
That would be, I see. So it's purely diagonal in K. So it just falls apart into separate Hilbert spaces in different Ks, right?
Yeah.
But why do you think that this would be relevant to cuprate? Because that would be just a Slater determinant in the momentum space. Like it just.
You see, that's what you would have thought, but it doesn't correspond to that. It gives rise to a Mott insulator if U is bigger than W.
So how does W enter into this game? I mean, if the if the
so
case
let me show you something. Yeah, let me show you something. Yeah, right here. Can you see this?
Yes.
Okay. You see this green function right here?
Yes.
Okay. When this term, so your green function is a sum, your density of states is a sum of 2 delta functions. And
yes.
when one of them, when the width of one exceeds the width of the other, it's a metal. When this term wins over this one, you end up with an insulator. Ultimately, the reason why this model is solvable is that this Hamiltonian is identical to the atomic limit of the Hubbard model.
Yes, exactly. Absolutely.
Okay?
Right.
So all that Hatsugai and Khomoto did is once you realize it's the atomic limit of the Hubbard model, well, the atomic limit of the Hubbard model has very non-trivial physics. But now you've done it in K-space, which means there has to be a width associated with where you have the metallic state and where the insulating state takes over. As you can see from right here, the bandwidth is right here.
Yeah, but these are all different, I mean, decoupled points. The fact that you decided to put them on a line, this is completely irrelevant. You could have
No,
point
it's
in
not.
K-space
No, it's not.
separately.
Okay, here is U bigger than W, N equals 1. Here is U less than W. These two bands now cross the chemical potential. And this is the metal, this is the insulator.
I see, okay.
Okay? And that's what people didn't really appreciate. And these bands disperse because you've added the kinetic energy.
Right.
Okay, I think that's a good exchange of ideas, and that could continue on by email or some other means. But we have some other questions we'd like to get to. So thank you very much for the question. Yashar, please lower your hand. Next person on the list is Jim Klein, professor in the Department of Physics. Jim, please answer your question.
Hi, that was a very interesting talk. Some years back, Shucheng Zhang and his collaborators had this SO5 theory trying to unify the high TC superconductivity and the anti-ferromagnetic behavior as a function of doping for these cuprate materials. Is there any link whatsoever between what your view is now and that kind of framework, or is it they just totally different?
Excellent question. My favorite number is 0. There is 0 overlap, and I'll tell you why. It's because what the Hatsugai-Khomoto model does is it completely divorces the Mott problem from antiferromagnetism. There is no magnetism in this model. Okay, the metallic state is completely degenerate. So the Hatsugai-Khomoto model does exactly what Mott had envisioned, that antiferromagnetism is just a confusion of the whole problem. And I think it's a confusion of the whole problem. And the gap is coming from some other mechanism. Now, the moment people have antiferromagnetism, they tend to use that as a crutch and extend it all the way to optimal doping. What do you think is wrong? There's no antiferromagnetism going on there. So whatever the mechanism is, it's something much more generic.
Thank you.
Sure.
Okay, thanks. The next question comes from Professor Brad Civic, who's a professor in both the departments of physics and chemistry. Brad, please unmute yourself and turn on your video. Ask your question.
Both done. So Philip, that was really exciting. First thing I'm going to do after I hang up is go download your paper. Believe me.
Thank you.
So my question has to do about, so normally if people discuss, the excited states of a Mott insulator at all, it's in this doublon holon picture, which is usually
right.
Which is usually given sort of a real space interpretation as doubly occupied and zero and unoccupied.
Yes, that's right.
And so you showed these two operators really quickly, and I'm wondering if you're saying that this is much better to understood in a moment.
Right. Okay. Now, excellent question. Okay. Now, if you go back to the Hubbard model, okay, the reason why the real space operators are problematic is that they don't diagonalize the problem. Okay, so you can write the spectral function in the Hubbard model as the holon part, doublon, but then there's the doublon-holon mixing. The doublon-holon mixing is this process right here, which is dynamical spectral wave transfer. There is no such term in the Hatsugai-Khomoto model, which means that these band operators completely diagonalize the problem and completely separate it. Okay, so the Hatsugai-Khomoto model doesn't have that complication. Now, what people generally, the assumption is that there is no interesting physics if in fact, now in the Hubbard model, there's no way of separating the Mott gap from dynamical spectral wave transfer. And what the Hatsugai-Khomoto model does is it separates these into two distinct pieces. So it's not as if these operators are better than the other ones. It's just that with this model, these band Hubbard operators completely separate the spectrum into two pieces which don't talk to one another. And that's not possible in the Hubbard model. Okay, I'm done.
So Brad, if you're done with the question, please lower your hand.
I don't have a rejoinder. I'm
no
I'm
problem.
done with the question. Thank you very much, Philip.
Okay, sure.
Okay, well, thanks very much. It doesn't look like we have any other extremely pressing questions, and actually we're at maximum time. It is now time for the après colloque, but before that, I will just remind everyone to tune in again next week when we'll have a double header. On Thursday, we'll have the Anna I. McPherson Public Lecture for 2020. It's going to be given by Nurjas Mavalvala, who is the Marble Professor of Astrophysics and the Dean of Science at MIT. She's going to talk to us about gravitational waves. I think the title is Gravitational Waves, A Window to the Universe, on Thursday evening at 6:30 p.m. Eastern Time. And on Friday, she will give a scientific talk, a scientific lecture, colloquium style, at the same time as our normal colloquium at 3:30 in the afternoon Eastern Time. So please join via YouTube or Zoom if you have the link. For those two events, they're going to be fantastic. So thank you once again, Professor Phillips, for an excellent talk. Everyone,
it was my pleasure. I hope it was understandable.
Keep saying good things. Thanks again.